Welcome to another deep dive. Today we're tackling the universe, its vastness, its beginnings, and whether there's more out there. A lot more. We got some fascinating material by Professor Brian Keating, so let's dive right in.
Yeah, Professor Keating starts by quoting Arthur C. Clarke. The only way of discovering the limits of the possible is to venture a little way past them into the impossible. It's a powerful reminder, I think, that imagination is key in scientific discovery.
It really is. Makes me think about, those old maps, the ones with "Here be dragons" scrawled at the edges. Humans have always been drawn to the unknown, especially when it comes to the cosmos.
And our understanding of the universe, it's changed so much over time. Think about Copernicus and Galileo. They really shook things up, right? Challenging that whole Earth-centered view.
Totally shifted us to a sun-centered perspective. Huge paradigm shift. It's like that moment you realize, wait, the Earth isn't flat. Professor Keating uses this analogy of the ocean horizon to explain the observable universe.
Right, right. So picture yourself standing on the shore, looking out at the ocean. You can only see so far. Yeah. The Earth's curve blocks your view. That's kind of like the observable universe. It's the part we can see from Earth, limited by how long it takes light to reach us.
So just like we can't see beyond the horizon, there's a limit to how far back in time we can see with the telescopes.
Exactly. What's really wild is that the observable universe is actually, well, way bigger than you might think. Like, it's estimated to be around 92 billion light years across, which, is a lot bigger than the universe's age of 13.8 billion years.
Hold on, how's that even possible? Wouldn't it take 92 billion years for light to travel that distance?
See, that's where space-time comes in. And the whole expansion thing, the universe itself is stretching, like the fabric of space is expanding. So as light travels towards us, the space it's moving through, that's expanding too. It means the light from those super distant objects has traveled further than its age would suggest.
So the universe is stretching, almost like I don't know, a rubber sheet.
Yeah, it's a decent analogy, but, space-time's a bit more complex than that. And it's driven by this force we still don't fully get. We call it dark energy.
Dark energy, another one of those cosmic mysteries. But okay, let's go back to the observable universe. How do we even know what the early universe was like? I mean, we can't time travel, right?
We have this incredible tool. It's like a cosmic time capsule, the cosmic microwave background radiation, or CMB. It's light that's been traveling for almost 13.8 billion years, from just 380,000 years after the Big Bang.
So it's like a baby picture of the universe, a snapshot of what things looked like way back then.
A great way to put it, yeah. And the patterns we see in the CMB, they aren't random. They give us clues about the early universe, support theories like the Big Bang and inflation.
Okay, I've heard about the Big Bang, but what's inflation?
So inflation is this period of super fast, crazy expansion, like right the first fraction of a second after the Big Bang. It's important because it helps explain some of the things we see in the universe that the Big Bang alone can't, like why it looks so uniform, so flat on a large scale.
So it's not just about the universe expanding, it's about this burst of insanely fast expansion right at the start.
Exactly. And the evidence for inflation is pretty strong, actually. The patterns in the CMB match what inflation theories predict really closely. It's one of the big reasons why the Big Bang theory is so widely accepted.
That makes sense. But what about the Big Bang itself? Like, what really convinced scientists this incredible event actually happened?
Well, there's actually a ton of evidence. For example, we see galaxies redshifting, meaning they're moving away from us. And that's what we'd expect in a universe that's expanding from a single point, like in the Big Bang.
So it's like a cosmic explosion sending everything flying outwards.
The Big Bang wasn't an explosion, not in the usual sense. It was more like the expansion of space itself from this incredibly hot and dense state. But yeah, the explosion analogy helps kind of visualize everything moving away from a center.
Okay, that's starting to click. But here's where it gets really wild. What if the universe isn't alone? What if there are countless others out there? Like, is there any actual science behind this whole multiverse idea?
It might sound like sci-fi, but the multiverse has roots in some theoretical physics. There are a few different types that scientists have proposed. For instance, one idea is that our universe is just one bubble in this vast cosmic foam with new universes constantly forming and expanding.
So like a cosmic bubble bath where each bubble's a separate universe. That's crazy. But is there any way we could ever actually prove that?
That's the tough part about multiverses. Really hard to test. But some scientists think there might be subtle hints in the CMB, like some of the weird cold spots we see. They could be caused by, interactions with other universes. It's controversial, but pretty exciting to think about.
Wow, so even the temperature of the CMB could hold clues about other universes.
It's a possibility, But it's important to remember this is all still very speculative. There could be other explanations for those cold spots. We need more evidence before we can say for sure.
This is already a lot to process. We've gone from an Earth-centered universe to an expanding one with maybe countless others out there. What a journey.
And we're just getting started. Professor Keating's work really shows us how much we're still learning. The universe is full of mysteries and surprises.
Speaking of exploring further, Professor Keating talks about what might be beyond the observable universe. Like, what are some of the ideas about that vast, unknown region?
Well, imagine we could travel billions of light years past what we can see, what we'd find. Well, it's a lot of speculation, really. Some scientists think it could just be more space, maybe infinite, filled with galaxies and stars and planets we can't even imagine.
Infinite space. That's mind-blowing. It makes you feel pretty insignificant, huh? But what if it's not just more of the same? What else could be out there?
There's this idea called the cosmological principle. It basically says the universe is like homogeneous and isotropic on large scales, meaning it looks pretty much the same in all directions and from any location. So if that holds true beyond what we can see, we might just find more of what's already around us. Galaxies, clusters, those big cosmic voids.
So more of the same, but on a scale we can't even grasp, like zooming out on a map and realizing, oh, there are whole continents I didn't even know existed. But could there be places where, like, the laws of physics are different?
Ah, now that's a fascinating question, and it's something physicists have definitely thought about. Some theories, like string theory, they allow for the possibility of different physical laws in different parts of the universe, or even in other universes if you're thinking about the multiverse.
So there could be a universe where gravity works backwards or where the speed of light is faster. It's like something out of a fantasy novel.
It is pretty mind-bending, I'll give you that, but we've got to be careful. We're getting into super speculative territory here. There's no evidence for that kind of stuff yet.
Right, back to reality. We've been talking about all this vastness, but let's zoom in on our own universe for a bit. Professor Keating talks about how the universe evolved, from the Big Bang to all the complex structures we see today. Can you walk us through that story?
Okay, picture this. The early universe just after the Big Bang. It's super hot, incredibly dense, filled with a sea of these tiny particles. As the universe expands and cools, these particles start interacting, forming more complex structures.
It's like a cosmic recipe, right? You start with basic ingredients and you end up with something incredibly intricate and beautiful.
Love that analogy. And one of the first big steps in this recipe, it's the formation of protons and neutrons, the building blocks of atoms. This happens just a few minutes after the Big Bang. We call it Big Bang nuclear synthesis.
So the very elements that make up everything around us, even us, they were created in those first few minutes.
Exactly. And as the universe keeps cooling, these protons and neutrons, they start sticking together. They form the nuclei of light elements, mostly hydrogen and helium. And the amount of those elements we see today, that's one of the big pieces of evidence for the Big Bang.
It's amazing. We can look at the composition of stars and galaxy and trace it back billions of years. But how did we go from a universe of just hydrogen and helium to the stars and galaxies we see today?
Well, gravity's the key player here. You see, there were these tiny density fluctuations in the early universe, amplified by inflation. These made some areas slightly denser than others. And over time, gravity pulls more and more matter into those denser spots. Eventually, those become the seeds of galaxies.
So gravity acted like a cosmic sculptor, shaping the universe into all these vast structures.
You got it. And inside those dense clouds of gas, stars begin to form. The intense pressure and heat at the cores of stars, well, that ignites nuclear fusion. That's the process that powers stars and creates heavier elements.
So stars are not only beautiful, they're also these incredible element factories, creating the stuff that makes up planets and ultimately life itself.
It's really quite remarkable. And when those stars reach the end of their lives, they explode. Supernovae, and those explosions scatter all those heavier elements back out into space, enriching the next generation of stars and planets.
A cosmic cycle of creation and destruction, each generation building on the last. Professor Keating also talks about this incredible image, the Hubble Deep Field. What can you tell us about that?
Oh, the Hubble Deep Field. One of the most profound images ever captured. The Hubble telescope was pointed at this tiny patch of sky, so small it's like looking at a grain of sand held at arm's length. And what it revealed was just stunning. Thousands of galaxies, each with billions of stars, stretching across billions of years of cosmic time.
It really puts things into perspective. We're just a tiny speck in this vast, incredible universe. But where do we go from here? What's next for this amazing cosmos?
Well, the universe is still expanding. And what happens with that expansion? That's one of the biggest questions in cosmology.
What are some of the possibilities?
One possibility is that it just keeps going, forever, driven by dark energy. We call this the big freeze. The universe gets so vast and cold that stars stop forming, and everything slowly fades to darkness.
That sounds a little, depressing. Are there any other options?
Another idea, though it's not as popular based on what we see now, is the Big Crunch. In this scenario, gravity eventually wins. It overpowers the expansion, and the universe collapses back in on itself. Ends in a singularity, kind of like the one it started from.
So it'd be like hitting the rewind button on the cosmos. Everything goes back to how it began.
It's a cool thought, but there's a bit of a problem. The Big Crunch would need way more matter than we actually see in the universe, and even if there was enough, it wouldn't necessarily be a perfect rewind. The laws of physics, as we understand them, they say that entropy, disorder, it always increases. So a Big Crunch wouldn't reverse everything perfectly.
Wouldn't that also kind of break the laws of physics as we know them? Like, how could the universe just reverse its expansion and contract back to a singularity?
You're right to question that. The Big Crunch is highly speculative, and it relies on some assumptions about gravity and how matter is spread out in the universe. If it were to happen, it would probably involve some very complex exotic physics that we don't fully understand yet.
Sounds like the future of the universe is still very much a mystery. We've talked about evidence for the Big Bang, how galaxies evolved, even the crazy idea of a multiverse. But are there other theories out there, alternatives to the Big Bang? Professor Keating mentioned that there are. Can you tell us more about those?
Of course, the Big Bang is the leading theory, but some scientists are exploring other explanations. For instance, there are cyclic models. These suggest the universe goes through periods of expansion and contraction, maybe even infinitely.
So instead of one Big Bang, it'd be more like a cosmic heartbeat, with the universe expanding and contracting over and over again.
Exactly. And then there are theories that look at a singularity-free start to the universe. They propose the Big Bang wasn't the absolute beginning, but rather a transition from a previous phase.
It's fascinating to think about these alternatives. It really shows how science is always changing. Our understanding of the universe can shift as we find new evidence and develop new ideas.
I completely agree. And we have to remember that even our most successful theories are just models. They describe the universe based on what we know right now. There's always room for them to change as we learn more.
Professor Keating's work really shows us how much is still out there. We've covered so much in this deep dive, but there's always more to explore. What are some key takeaways you'd like our listeners to walk away with?
I think the most important one is that sense of wonder and awe. The universe is this incredible, vast place, and we're only beginning to scratch the surface of understanding it. The Big Bang, galaxies forming, the possibility of multiverses, the mysteries of dark energy and dark matter. There's so much to discover.
Couldn't agree more. And I think it's important to remember you don't need to be a scientist or astronomer to appreciate it all. Anyone can look up at the night sky and feel that sense of wonder, feel connected to something much bigger than ourselves.
Absolutely. And that sense of wonder can push us to learn more, to ask questions, to keep pushing the limits of what we know.
Before we wrap up, is there a final thought you'd like to leave our listeners with? Something to ponder.
What if space and time really are infinite? Like some theories suggest, what does that mean for what's out there? Could there be infinite universes, each with its own laws and its own amazing stories unfolding?
Wow, that was quite a trip through the cosmos. I feel like we've covered billions of years and billions of light years in, what, like an hour? It's amazing how much we've learned about the universe. But it also makes you realize how much is still out there, how much we still don't know.
Yeah, it's like we've just dipped our toes in the water. Every new discovery just opens up more questions, more mysteries. It never ends, which is what makes it so exciting.
So let's try to recap some of the big things we talked about today. We started with how important imagination is for science, right? If we hadn't dared to imagine a sun-centered solar system or the Big Bang, well, we'd be stuck with some pretty outdated ideas.
Absolutely. And we talked about the observable universe. That's the part we can actually see from Earth, limited by the speed of light and the age of the universe. But even that observable universe is mind-bogglingly huge. 92 billion light years across.
And within that observable universe, we see evidence for the Big Bang everywhere, right? Redshifting galaxies, the abundance of hydrogen and helium, and then there's the cosmic microwave background radiation. All these things point to the Big Bang as the best explanation we have for how it all started.
Right, and then we jumped into the deep end, so to speak, with the multiverse. The idea that our universe is just one of many, maybe with different physical laws and constants in each one. We don't have proof yet, but there are some tantalizing hints out there.
We even speculated about what might be beyond the observable universe. More space, something completely different, who knows?
And of course, we can't forget the epic story of how the universe evolved. From the hot, dense early universe to the formation of galaxies, stars, planets, it's a story that's still unfolding, and we're lucky to be a part of it.
I think Professor Keating's work really shows us the importance of asking big questions, even if they seem impossible to answer. It's how we learn, how we push the boundaries of what we know.
I couldn't agree more. And as we explore, we should never lose that sense of wonder. That's what drives us to keep looking, keep searching, keep discovering.
So, to all our listeners out there, if you're feeling inspired by this deep dive, keep looking up at the night sky, keep reading, keep asking questions. The universe is full of amazing things waiting to be discovered.
And don't forget the power of your imagination. Like Professor Keating said, sometimes the most incredible journeys start with a simple question. What if?
Thanks for joining us on the deep dive. We'll see you next time for another adventure into the unknown.